Hello again and welcome back. Let's kick off this project with the clock module. What you see here is the CPU clock reset board from the Pony80. Over here is the CPU, the z80. This is the reset circuit using a 555 chip. This is an inverter providing the slow clock circuit, and down here is a 6 MHz clock oscillator providing the fast clock. These two clocks are selectable using this jumper. I have a set of pins that I can use to hook up a reset indicator LED, a clock LED, a reset switch, and a halt indicator LED. But today I'm going to focus on the clock circuit. On the surface, the clock is a very simple device, but it has a huge impact on how speedy the computer is. It creates a constant timing signal, a continuous series of ones and zeros or on and off. This coordinates all of the chips so they work together perfectly. You can think of the clock as the beat in music. Musicians use the beat to stay in time with one another, creating music that is pleasing to the ears. If they did not stick to the beat, it would quickly become a mess of noise. The clock must include the ability to switch on and off quickly and cleanly, generating a square wave. It must also be capable of fanning out to all of the chips that will be connected to it. Otherwise, you will get a degraded clock signal and it may not function as desired. I have a few circuits that I've built to demonstrate different kinds of clocks. As I go through the circuits, I'll describe all of this in more detail. This first one is a 74 HCT14 Schmitt trigger inverter with a resistor connected between the input and the output and a capacitor connected between the input and ground. Before I get into how the circuit works, I want to explain the difference between a normal inverter and a Schmitt trigger inverter. If you look at the datasheet of a normal 74 HCT04 inverter, you will notice the high level input voltage. This is the voltage at which the input switches on. In this case, it's 2 volts. If you look at the line below that, you see the low level input voltage, which is the voltage at which the input switch is off. In this case, 0.8 volts. Now let's look at the datasheet for the 74 HCT14 Schmitt trigger inverter. There's a key difference with these values. Notice they are named a bit different: positive going threshold and negative going threshold. The positive going threshold indicates the voltage that the input switches on when the voltage is rising, and the negative going threshold indicates the voltage that the input switches off when the voltage is decreasing. Let me draw it out. Okay, I'll start with the HCT04. Yeah, 04. I'll add the 2 volt threshold up here and 0 volts down here. Now when we power on the circuit, the input is off. And so then as our input starts rising, it hits that threshold of 0.8 volts. And up until then, it's been guaranteed to be off. But now as it rises through 8 volts, all the way up to 2 volts, where it turns on, we're in a state of unknown. It could be on or it could be off. We really do not know. And then as we start heading back down under 2 volts, it's back into that unknown area, and until it hits 0.8 volts again and then switches off. So there's these points of the unknown. We don't know whether it's on or whether it's off, and that causes a problem for clocks. But let's look at the HCT14. Now I'll put 1.7 volts up here. That's the threshold, and then I'll put 0 volts down here, and I'll add the 1 volt threshold or somewhere right around here. Let me move this so you can see it here. Okay, so now when the power is on, we start at 0 volts, and as it rises up past the 1 volt threshold, nothing happens. The input continues to be off. It avoids that unknown because it hasn't yet reached the positive going threshold at 1.7 volts, where it does then turn on. Now it could keep going up and then come back down, and as it goes through that 1.7 volt threshold again, nothing happens because it's moving down. So it keeps on falling down, and then once it hits that 1 volt negative going threshold, then it switches off. And so you get rid of that unknown area that we have up here and here. So this makes it perfect for our clock since we have to have square waves. Now back to our circuit. When power is applied, the input is in the low state and the output is in the high state. Since the input and the output are connected with the resistor, the capacitor connected between the input and the ground begins charging through this resistor. Once the voltage reaches the positive going voltage threshold on the inverter, which is 1.7 volts, the input will turn on. As this input turns on, it turns off the output. Then the capacitor begins to discharge, reaching the negative going voltage threshold on the inverter, about 1 volt, and turning off the input. So how do we figure out which values to use for the resistor and the capacitor? Well, there's an easy formula for figuring these out. Frequency equals 1 over the value of resistor in ohms times the value of capacitor in farads times 0.67 for the HCT14. Since we want to specify the frequency, we need to change this around a bit to calculate either the resistance or the capacitance needed. I'm going to start with an arbitrary capacitor value since capacitors have fewer standard values. I'm going to use a 4.7 microfarad as it's one that I have on hand. So we convert that to farads, and then we'll use this formula to calculate the resistance. And the resistance is going to equal 1 over the frequency, and in this case the frequency that we are going to use is 5, but I'm just going to write out the formula and then we'll convert everything over. So 1 over 5 divided by the product of the capacitance, which in this case would be the 0.000047 times the 0.67. You could also start out with a predetermined resistance and then calculate the capacitance needed with this formula. And that's basically the same thing, but switching the C and the R. So capacitance equals 1 over F divided by the product of resistance times 0.67. Okay, so let's build a clock that generates a signal with a frequency of 5 Hertz. And we know that our starting capacitance is 4.7 microfarads, but in farads it's expressed as 0.0000047. So if we divide 1 by 5, we get 0.2. So our 1 divided by our frequency is 0.2. And then if we multiply our capacitance times 0.67, so 47 times 0.67, we get our, let's change the digits here, hold on, we need more room. We get 0.00003149. So capacitance times 0.67 equals 0.00003149. All right, and now if we divide the 0.2 by the 0.00003149, we should get the resistance needed. And there you have it. Let me remove the 2 decimal points here. And you have 63,512 ohms to generate a 5 Hertz signal. Now, I don't have a 63,512 ohm resistor, so I'll probably just round down and make it a 56K resistor. So let's get our breadboard set up. We'll insert the inverter and the power and ground. And then we'll place a resistor between the input and output, 56K resistor, and then the 4.7 capacitor to ground. And then for demonstration purposes, I'm going to plug in an LED and a current limiting 1K resistor, just so we can actually see something happening. There we go. Plug this in here, we should see a light flashing. Oh yeah, and there you go. I've got my oscilloscope connected to the output, so let's take a look at what we have produced. You can see a very pronounced square wave. Let me adjust that. You can see a very pronounced square wave. There we go. And if you take a look at the min and the max voltages at the bottom left of the screen, you can see it going from a few millivolts to just over 5 volts. And if you look at the bottom center, our frequency is 4 Hz. This is most likely due to the tolerances and variations within the components themselves. Now move the probe to the input, and you can see how the voltage is ramping up and then back down, creating a triangle wave. You can see that when the upward slope hits 1.64 volts, the output switches off, causing the input voltage to fall. Then when the voltage drops below 1 volt, the output switches back on. I mentioned earlier about fan out. This term refers to the number of chips that can be connected to the clock output at the same time. In our case, we will connect chips such as the CPU, the PIO, keyboard interface, and others. We need to ensure that the chip we utilize for the clock can support being connected to all of those at the same time. If we look at the datasheet for the HCT14, it states that it is capable of driving 10 LS-TTL loads. LS is the chip family, and TTL stands for transistor to transistor logic. So we should be able to connect 10 chips without signal degradation, but more on this later. Another type of clock circuit utilizes a 555 timer chip configured as an astable multivibrator. That's just a fancy name for a circuit that's not stable either on or off and oscillates between the two states. The red outline shows the boundaries of the chip, so I can show how the chip itself works along with the components I've added. The chip is made up of 2 voltage dividers in serial, with the threshold voltage being 2/3 of the input voltage and the trigger voltage being 1/3 of the input voltage. The threshold voltage is connected to the negative side of a comparator, while the positive is connected to pin 6, the threshold pin. The trigger voltage is connected to the positive side of another comparator, and the negative side of this comparator is connected to the trigger pin, pin 2. The 2 comparators feed into the SR flip-flop that's connected to the output. The discharge pin, pin 7, connects to the ground when the output signal is low. So here's how it works. When power is applied, the capacitor and the trigger and the threshold are all in the low state, which means that the output is high, turning off the discharge pin. So the 5 volts charges the capacitor through resistors A and B, and the larger the resistance or the bigger the capacitor, the slower this will change. When the charge hits 2/3 of the input voltage, the threshold comparator will flip the output to off, enabling the discharge pin. This connects the capacitor to ground through resistor B. When the capacitor drains to 1/3 of the input voltage, the trigger comparator turns the output high, turning off the discharge pin and allowing the capacitor to start charging again. Again, we'll turn to math to select the values that we want to use to generate the 5 Hz signal. For the 555, there are a few formulas we can use. We can control the time the output is on and the time that the output is off. The formula for the time on is 0.693 times C in farads times RA plus RB in ohms. And the formula for time off is 0.693 times C times RB. Remember, we're only going through that one resistor when it's going off. We're going through the other 2. And the total time, if we wanted to calculate that, is 0.693 times RA plus 2 RB times C, the capacitance. And to get the frequency, we would simply divide 1 by the total time. So it's 1 over 0.693 times RA plus 2 RB times C. You could also prefactor the 1 over 693 and divide that out, which gives you about 1.443. And then you can use that to determine the frequency with this formula, which is 1.443 divided by RA plus 2RB times C. So let's plug some numbers in here now and calculate the resistance that we need to reach our frequency. So let's start again with the capacitor and choose a 4.7 microfarad. So we have C equals 0.00000047, and the frequency we're looking for is 5 Hertz. So we use the formula for frequency, plugging in the capacitor values and 5 Hertz for the frequency. But as you remember, the formula is 1.443 over the resistance times the capacitance. But we don't know the resistance. That's what we're trying to find out. So let's flip this around a little bit and set the frequency up here. So we want 1.443 divided by 5, which equals 0.288. And then if we take that number and divide it by our capacitance, the 0.000047, we get about 61,276. Running out of space here. So let's move this up here. So we don't have a 61,276 ohm resistor. So I'm actually just going to divide that by 3, because we got to take that extra RB out of there. And we get about 20,000 ohms per resistor. So I don't have 20K, so I'm going to use 22K, and we'll see how that ends up. And we'll put it on the breadboard and work with that. So I've got my breadboard here. Let's go ahead and put the 555 chip in here and hook up the power and the ground. Be aware that on the 555, the power is pin 8, like in most chips, but the ground is on pin 1, not on pin 4. Now I'm going to connect pin 2, the trigger, to pin 6, the threshold. And now I'm going to add resistor A between pin 7, which is discharge, and pin 8, which is 5 volts. That's where we get our power to charge the capacitor. Then add resistor B between 7 and 6. And finally, add the capacitor between pin 6 and the ground. These are the 3 parts that will set the frequency. Now if we look at the 555 datasheet, there is a note about pin 5. It says that decoupling control voltage to ground with a capacitor can improve operation. This should be evaluated for individual applications. Well, I'm going to go ahead and put a capacitor there, 0.01 microfarad between pin 5 and the ground. There we go. And pin 4 is a reset, which pulls discharge low, draining the capacitor. This is an active low signal, so we want to force this high to keep it from resetting on us. So we'll just connect it to 5 volts. And now I'll hook up an LED and a current limiting resistor to show the clock signal. Now if I plug this in, we should see a signal similar to our inverter signal. And there we go. The last circuit I want to discuss is the clock oscillator. This is a TTL compatible chip that provides us with a clock signal with few external components. So I'll put it on the breadboard and I'll hook up power and ground. And then I'll hook up an LED and a current limiting resistor. This won't be as exciting because this is a 1 megahertz clock oscillator, so the LED will pretty much look like it's staying on. But when we get to the oscilloscope, you'll see the output. All right, let me plug this in here and you should see it light up. And there it is. So when we look at it with the oscilloscope, we can clearly see the square wave, although capacitance on the breadboard is causing some noise. But notice the bottom center that the frequency isn't even 1 megahertz. By the way, I have a link in the description below for this oscilloscope. I purchased it on Amazon and I'm really happy with it. I do make a commission on the sale, but that's not related to the scope itself. It will just help me to pay for my obsessive hobby. Well, this wraps up the video on clock circuits. We've seen the different types of circuits and how they function. The Pony80 uses the inverter for its slow clock and the clock oscillator for its fast clock. It also uses the 555 chip to hold the reset signal low for a couple of seconds to give all of the chips on the backplane a chance to reset, but we'll get to that in a later video. Next up, we'll talk about the Z80 and its architecture. Thank you to all who subscribe and like my videos. This is a new undertaking, and it takes a bit more than I ever thought. And if you haven't, please like and subscribe, and don't forget about my Patreon page or my website. The website will be the place that I put the companion schematics for these videos. All the links are in the description below. Have a great day.